My research is over the soil moisture monitoring with using a drone, right? The idea is, right now, soil moisture sensors are extremely inconvenient because you have this antenna that sticks out of the ground as well as equipment that is buried really close to the soil, right? So the issue that this causes is that with your tractor, or with the farmer's tractors and his equipment that he uses to plow, till, cultivate, anything like that to his fields, this equipment can damage those sensors. So what we tried to do was we tried to come up with a solution where this is no longer an issue. So what we did was we created a soil sensor that we buried a foot into the ground, and then we have this drone here that we mounted the receiving equipment to, and we receive packets of data from that buried soil sensor. So on these heat maps, you can see the signal strength that we measured, which was the key here. We measured soil moisture, but we wanted to make sure that we could make a connection, so the soil moisture was just that we had data to send. Really, we were focused on the connection made between both the transmitter and the receiver. So on these heat maps, you have parallel polarization and cross polarization. Parallel polarization is when you have your antenna aligned, but cross polarization is when they're misaligned, 90 degrees, right? So what you can see from these two heat maps is that they perform relatively the same, which means that our system, which this is great, our system is not sensitive to calibration or antenna misalignment. So in the very center of the heat map, you can see that there's a yellow or a more yellow color. And on the edges, there's a darker blue color. The yellow color represents a stronger signal value. And this is important because the stronger signal is how you communicate data. From the center, we traveled about 100 feet in each direction, and we're able to successfully communicate data.
What's your name?
Levi.
What's your tribe?
I'm an Eastern Shawnee.